Just a couple of words before I begin. This is a pretty condensed presentation. There's a lot in here because there's a lot to say about titanium dioxide. Um, the program that I want to show you, basically, I want to talk to you about the history and the development of the TO2 technology in the market, so I can give you an understanding of that. Then explain how titanium dioxide works, how it creates opacity, and how it needs to be utilized in both water and solvent-based systems. Then I want to talk about the other effects of TO2, not just on opacity, the side effects or the other things like coatings and gloss and durability and flocculation. And then finally, some comments on formulating and optimizing TO2. This is by far from exhaustive, okay? And there'll be many questions that people have. We'll try and deal with as many as we can at the end, but I would invite people to follow up with questions with emails if they feel so the need. I'd also like to say thank you to the people from Venator who have allowed us to use several of the images in this presentation, and also to Paul Dietz, who's a technical director at FP Pigments, who has a 20-odd year experience with Venator and who is also co-responsible for this presentation. And essentially, it couldn't have been put together without Paul. So I'll move on now and plow through the data. There's a lot to talk about. Everybody will be finding it interesting. So first of all, to talk about titanium dioxide, the fundamental thing about titanium dioxide, and although this doesn't really impinge on its history, it's a rutile titanium dioxide is only used because of its ridiculously high refractive index. Okay, there isn't any other material known to man that can be made in large quantities that isn't poisonous. And I'll talk a little bit later about why that's important and how it works. But it's the uniqueness of titanium dioxide that has caused the product to develop into such a massive global product that is vital to the coatings and plastics industry, especially the coatings industry. When we talk about the history, you know, TO2 was discovered at the end of the 19th century, but the actual industrialization of TO2 happened really after the war, when people moved away from the poisonous lead pigments into titanium dioxide, which was seen as an inert pigment which had a high refractive index. And you can see from this graph here, as the industrialization happened, we started off with the sulfate process, and then in the 1950s, DuPont started the chloride process, and you can see the growth in titanium dioxide volumes in thousands of tons. So by the 2000s, we were up to 5 million tons. We're actually up to over 7 million tons of TO2 globally now. And I think the projection is that by about 2030, there'll be 10 million tons of titanium dioxide used globally. And just to give you a feel for how that evolution in titanium dioxide happened, drawn a little map here of where the plants were. You know, back at about 100 years ago, titanium dioxide was born in Europe, largely in the UK and Germany, and in the United States. And so that's where all of the production was up until the start of the Second World War. Then after the war, the larger industrialization of the material took place. You got multiple plants built in the United States, a small plant in South America, many plants in Europe, the one plant in South Africa that some people may remember, and plants in Australia to serve the Asian of ore down there. Now, as you move from the 80s towards the 2010, you see probably a similar development, but the start of the growth in Asia, where because of the growing economy in Asia and the moving from being third world countries to next world countries, titanium dioxide usage grew and grew and grew in these areas. And so there started to be the first plants in China, plant in Taiwan, plant in Malaysia. Okay, there was a plant in in Saudi Arabia, and of course the plant in South Africa at that point closed. But the most dramatic thing when you think about what's happened with the TO2 market is what's happened since 2010, where essentially several plants, older plants around the world have actually closed, and all of the development of titanium dioxide has taken place in China. To the point that at the 7 million tons that's made and consumed now of titanium dioxide in the world, getting on for half of it is made in China. Probably just more than half of that is consumed in China, but the rest of it is exported around the world and is consumed by many countries and many places. And just to give you an idea of how it's broken down, this is the production. And as I said, China is about 47% titanium dioxide production worldwide now. There's still a lot in the EU, there's still a lot in the US. But when you can see this growth in Chinese, especially sulfate processed titanium dioxide, it exploded around about 2005, 6, 7, up to where we are now, towards the present day. So many of you who are in the African market, if viewers here are African, will probably be getting imported material either from the US, either from Europe, or from China. Now, to give you an idea about where the titanium dioxide is being used, I don't want to spend a lot of time talking about the market, but for the 7 to 8 million tons that there will be between now and the end of 2025, I color-coded the markets based on a rough size and how fast they're growing. In North America, Western Europe, Japan, and Australia, the titanium dioxide markets are largely mature. The growth is very, very limited to probably just a very small digits close to GDP. However, in almost all of the other areas, titanium dioxide is growing rapidly, faster than GDP. It's seen as a quality of life product, and you'll probably find those of you in the coatings industry that the coatings markets are growing slightly faster than GDP too, because people want cars, fridges, they want new houses. And so as general standards of living increase, so does the use of titanium dioxide, which is why the explosion in Africa, Asia, and the Far East. So moving on from the market, there are two processes for making titanium dioxide, or two fundamental routes. There's the older fashioned, what we would call the sulfate. The first version of this technology goes back to the 1950s, the chloride route. And there are some very, very big differences in these two technologies, and it's important that as the user of the pigment, you understand these differences. So I'll spend a little time going through that here. Again, it's a little bit quick, but hopefully you'll get a good understanding of what the fundamental differences are. Essentially, the sulfate route is called as such because the digestion of the ore is done with sulfuric acid. Okay, so you're taking an iron-based titanium-bearing oxide ore, consuming it in sulfuric acid, reducing it, then purifying it in the next stage, and then bringing it back to the titanium dioxide form via hydrolysis and then calcination. The chloride process uses totally different ores in general that tend to be a lot higher concentration, and chlorine is the reactant here. Coke is the reducing agent. And so essentially you end up with, again, a largely iron-bearing ore, but you react carbon to get titanium tetrachloride, which you then purify of iron and other impurities, then you oxidize it back to get the titanium tetrachloride and recycle the chlorine. That's the basic difference between the two processes, which sounds fairly simple. But when you try and understand the nature of the plants that you have to build to do this, it's quite startlingly different. Now, essentially, I'm going to go through this very quickly because the differences aren't important, but it's the scope of the difference that I'd like you to understand. The sulfate process, you start with ilmenite titanium or titanium slag. You have to dry it before you can use it. Before you react it with sulfuric acid, you have to make sure it's the right particle size for the reaction. Otherwise, that reaction you won't be able to manage it properly, so you have to ball mill it. Having ball milled it, you're going to digest it in sulfuric acid. You're going to add scrap iron to reduce it to the right oxidation state. You're then going to settle out the silicas and the impurities and things like this. You're then going to crystallize the iron sulfate and remove the copperas, which is the iron sulfate hexahydrate. Centrifuge that out, so you end up with and filter everything else off, so you end up with a titanous sulfate as pure as you can get. Then hydrolyze it, and then from the hydrolyzation tank, after you've washed it and treated it, you're going to dewater it, and then you're going to put it into a rotary calcination oven, great big oven about the length of a car park, that will gradually, at a temperature around about 1,000 degrees centigrade, produce the tiny titanium dioxide crystals. It all seems pretty complex. When you look at the chloride process, you're looking to achieve exactly the same end, small titanium dioxide crystals, but essentially you start off with a different ore, a higher quality ore, generally rutile. You can use titanium slag. And you put this into a chlorinator, which is a specially designed fluid bed reactor, which is about the size of a small 2 or 3 or 4 story building, and has essentially chlorine, coke, and very, very high temperatures where the reaction takes place to produce all of the chlorides of these materials. Now, these are purified via a process that I would liken to the sort of fractionation that you think about that they use in the petrochemical industry. It's not exactly the same as that, but that's the best way to think about it. So you can remove the chlorides that you don't want and keep the titanium tetrachloride that you do. And that then goes away stored and is often sold. Yeah, all titanium metals are made from titanium tetrachloride. So there's another market for that titanium tetrachloride from the chloride route, as well as using that titanium tetrachloride to oxidize by putting it into a reactor. Now, this reactor isn't 3 stories high. It's about the size of a small car, where you react with oxygen and essentially burn the titanium tetrachloride, cooling it in a the raw titanium dioxide that's produced in a very controlled way to produce the particles of just the right size and recycle the chlorine. So at the end of this process, you end up with very small titanium dioxide particles, but via an almost entirely different route. Both processes, when you've made the TO2 particles, they're then essentially, you could say, the same. And they go on to a wet treatment process. And I'll talk to you in detail about the types of treatment in a few minutes' time. But essentially, the uncoated TO2 from either process has to be wet milled, because lots of these wonderful little particles will stick together when they're in the either cooling down for the chloride process or running down the oven in the process. So you want to actually deaggregate them. So you'll put them through a wet mill. You'll then put on the surface treatments in the coating tank, and you'll then have to remove the water, wash it, remove the soluble salts, dry it, and then mill it again before you pack it. But this process, this back-end process, is the same for both the sulfate and chloride process. But it's not altogether surprising that a titanium dioxide plant, therefore, is quite big, quite expensive, and requires a lot of investment to make. Now, I'm not going to read all the way through this slide, but essentially this summarizes the big differences between the sulfate and the chloride process, because there are both differences in the operational costs, the investments, and the quality and environmental impact of both processes. The sulfate process uses cheaper raw materials, but the capital investment is generally lower because the plant's technically easier and the technology is more accessible. However, when you use the sulfate process to make titanium dioxide, the purification process is not as efficient as the chloride process. So you tend to leave some of the chromophoric metals like iron, manganese, chromium, niobium, some of them still in the pigment, which is why especially poor quality sulfate process pigment can often be ever so slightly different slightly yellowish color, and can be probably not some of the chloride process pigments. In addition, the nature of the calcination with the rotating calcining oven is so slow that you often get hard agglomerates, and so the particle size of the sulfate process pigment is sometimes not as good as chloride. And also, you always leave a little bit of anatase in sulfate process pigment, which means that can have an effect on durability. And as you probably saw from the very first slide I showed on refractive index, the anatase TO2 is not quite as light scattering as the rutile. So again, that's another reason why sulfate is maybe marginally down on some of the rutile products. In terms of the environment, the sulfate process requires a lot of energy for the calcination, and using an ore that's cheaper and has a lot of iron in it, using ilmenite, for every 1 ton of TO2 produced, you're going to produce a ton of iron waste. And there are limited markets for this material, although they've been saved in recent years by the amount of iron needed for electrical vehicle batteries. But even then, there's a lot more iron produced than the world can use. Chloride process, the ores are more expensive, the plants are more expensive, the engineering costs are higher, there's patents that cover the technology, so only a limited number of people can enter. The distillation process, I'd say, which purifies titanium tetrachloride, will result in better color and a purer product. And the rapid nature of the oxidation will give you a better particle size, better tinge strength, color, undertone, and opacity. So in general, you tend to find that chloride process pigments are slightly better and tend to be used in the higher end applications. With regards to the environment, the energy requirement for chloride tends to be as high, if not higher, than sulfate because of the high temperatures involved. Disposal of iron chloride waste can be an issue, but there are some exceptions to that, but there's a lot less waste than sulfate. But a lot of the chlorine is actually recycled. I should be fair to sulfate and say in certain of the European plants, especially, a lot of the sulfuric acid is recycled as well, where they've developed the technology, especially in Germany, to do this. Overall, however, the carbon footprint when they do a cradle to gate of a chloride process tends to be a little lower than sulfate process, but the sulfate process plants, depending on if they have acid recycle or not, significantly different titanium carbon footprints. The Titanium Dioxide Manufacturers Association has basically shaken hands and agreed on a single number of about, I think it's 4.9 tons carbon per ton TO2. That is done from all types of titanium dioxide as an average. But the range is probably something like 3.2 to 8, depending on the plants. So moving on to the second stage, now let's talk about what TO2 is and how it works and why you use it. I'll come back a little bit to the surface treatments and what they are as we go through this, okay? But you remember, I spoke to you about refractive index at the very beginning, and that's why we use titanium dioxide. So you have to think about, you use titanium dioxide in coatings because of wanting to provide opacity or hiding power. And that's the ability of a substance or a coating to obscure the substrate. So if you just imagine, if you've got a transparent materials, you're looking straight through the coating and you're seeing the substrate, okay? If you've got completely absorbent materials, like if you've got lots of carbon black or black iron oxide, you can actually absorb all the light and not see the substrate. So that's a way of providing opacity without scattering the light. But if you want something to appear white, you have to scatter and bend all of the incident light back out. So the human eye is actually not seeing anything absorbed by the substrate. You actually see all of the light that's reflected. And that's what you're trying to achieve with titanium dioxide. You're trying to bend the light back out of the film, back into your eye before you see it. And it's worth thinking when you think about how titanium dioxide works, about how we see white things in nature. We see here some foam in a waterfall, or a polar bear, or an Arctic fox. They're all white. How do they appear white? What is whiteness? It has to be the scattering of all wavelengths of light. Otherwise, you'd see what was underneath. In the case of the waterfall, you're looking at different bubbles of air in water or different droplets of water in air. Refractive index of water and air is 1, water is 1.3, so there's a refractive index difference of 0.3. The light is being bent by multiple times by the many, many small particles, just in the same way as we explained in the previous slide, and so that you're seeing white light reflected back to you and you see whiteness. It works in a slightly different way, but the mechanism's still the same. Polar bears' hairs are made of keratin, which is actually hollow. It's kind of almost like a plastic polymer. And essentially, so you have a refractive index of the keratin is 1.5, the refractive index of the air is 1, the difference of 0.5. And isn't evolution wonderful? The hairs are hollow, so you get 2 points of reflection on the way in and on the way out. So you get much more efficient light scatter and you see white light. Interestingly, when a polar bear gets wet and you end up with water filling the holes in the air, you can actually see the legs are darker here, simply because the refractive index difference becomes smaller, because you actually have water instead of air between the hairs of the polar bear. So moving back to TO2, what you're trying to do is to have multiple light scattering events. So you bend the light out of the film and back towards the eye. So you have titanium dioxide giving you whiteness and opacity. If you tried to do this with a material with a low refractive index, like a calcium carbonate, which has a refractive index of 1.6, the polymers all have a refractive index of 1.5, you would actually see transparency. Okay. Now, in reality, what happens with TO2, and it's worth just to re-emphasize this, this is one of these wonderful Venator images that we got hold of, is that this is a side image of a paint film with all the titanium dioxide crystals there. So what's actually happening is the incident light is actually being multiply scattered, so that most, if not all, of the light gets scattered back out of the film towards the eye. Now, accepting that, when you think about, therefore, how titanium dioxide is going to work, the size of the particles and the efficiency of the particles and where the particles are starts to become important. And it's well known as some really decent science. I think it's called Weber's law, which defines that for a material of a certain refractive index, if you can define the particle size it needs to be at to scatter a certain wavelength of light. And for titanium dioxide, that particle size is approximately 280 nanometers. Okay. So all of the grades of titanium dioxide, whether they're chloride or sulfate, are generally, for those used in coatings to give whiteness and opacity, they're produced at around about 280 nanometers in size. I'll talk a little bit about the variations on that in a minute. But the reason for that is to scatter the light to the maximum effect with the minimum number of particles. But also, when you're thinking about this multiple scattering event, where the particles are in relation to each other is also important. If all the titanium dioxide particles are flocculated or stuck together, they're not going to scatter light efficiently as those that are evenly distributed within the paint. And science over the years has been able to show that the optimum distance for titanium dioxide light scatter is around about 1 particle size apart, or 300 nanometers. So if you can imagine, it's like a chain reaction. You want to have your photon of light hit a titanium dioxide, get bent, then hit another one before it passes further through the paint. And so when you think about how titanium dioxide needs to function, dispersion of the titanium dioxide and the stability of the dispersion, if you assume that the particle size is the right size in the first place, is really, really important. And so you can imagine, if you have titanium dioxide crystals too close together, there's no path of light between them. So they behave like one particle. if you have titanium dioxide crystals too far apart, whole wavelengths of light can pass between them and not interact. And so what you wish to have is titanium dioxide particles of the right particle size, approximately 1 particle size apart. It's that philosophy and that technology on which the FP Pigments particle product, that I'll only mention one at a time in this product, is this presentation is done. The rest is all about TO2. So knowing that you want to have titanium dioxide of the right size and titanium dioxide that is dispersed in the right way, and I want to talk about the way the different grades of titanium dioxide are put together and help you to understand how that technology has evolved so that you can use it in your coatings in the most optimum way. So I said we talk about the crystal size of TO2. Typically, for, as I said, opacity in a white coating, as such, the titanium dioxide needs to be at around about 280 nanometers. There are other versions of TO2. There's the buff titanium dioxide pigments that come in at plus 400. And there's also anatase pigments, which are used for specialist applications that to be as optimum for anatase at its different refractive index, they need to be at just below 200 nanometers. There are also some ultrafine and transparent titanium dioxides that lived for a while in sun creams, but I think are now used in photocatalytic applications and as catalysts. And these are even smaller, almost nanomaterials. But the one that we're focused on for coatings is the one at 280 nanometers. Okay. And you'll find that on every data sheet that you look at, the D50 will be targeted at somewhere around about 280 to 300 nanometers is the target norm. Anything outside of that, and it won't perform optically. But having made the titanium dioxide pigment and made sure it's rutile and made sure it's the right particle size, why not just use it as it is? Why do we have to have all these surface treatments? What are they for? What are the different grades all about? If TO2 is left untreated, you'll end up with poor wetting, simply because the crystal surface of the TO2 doesn't lend itself to being to associating itself with dispersions and polymers. You'll end up with inferior dispersion. You'll end up with problems with dispersion stability and flocculation, and ultimately viscosity stability. Without the surface treatment of the TO2 itself as an optical opacifier is pretty useless. If you have these problems, you're going to see a reduction in opacity, a reduction in gloss, a reduction in tinting strength, and a reduction in whiteness and color. And those are the only reasons you use the TO2 in the first place. So essentially, the surface treatment of the TO2 is vital in delivering, first of all, dispersion stability and being so that you can actually put the TO2 into whatever, because there's different surface treatments for different applications, but into whatever media it needs to go in, and then achieving that spacing of the TO2, that good stable dispersion that when the coating dries is going to give the light scatter that you require. So what are the types of the TO2 coatings and how are they applied? Imagine here we have a rutile crystal. It's essentially your angular rutile crystal. There may be a little bit of alumina inside it, especially if it's chloride, which is used to help with the durability. But generally, the inorganic coating that's on the outside will be applied at somewhere between a 1 and a 15% of the total weight of the TO2 supplied to you. I'll talk in detail about these different types. There's aluminium oxide is used, silicon is used, zirconia is used. So then hydrous TO2 and phosphate is also used in order to adjust the surface properties. So essentially, you have your inorganic coating, probably in multiple layers. Okay, there are certain super durable TO2s where the silica coating will be added several times in order to give multiple dense layers and therefore control the properties of the TO2 in detail. But having applied these inorganic coatings, for coatings in general, there's also an organic coating that is added. And this is normally a polyol, most often is trimethyl or propane. It's added at the milling stage during the TO2 production, and it improves the dispersion in the application, especially in solvent-based systems. It also improves the milling, and so the TO2 producers like to use it. Now, when you think of these inorganic coating examples, just want to give you some idea about what they're for. You'll find that on almost every single grade of titanium dioxide, there is some alumina. Okay, alumina is there to significantly improve the dispersibility and the dispersion stability. Now, alumina is not just Al2O3. Aluminium oxide has 9 different crystal forms that have radically different shapes and sizes. And the titanium dioxide manufacturers over about 50 years have developed a finesse in the use of these different types of alumina to change the nature of the surface of the TO2 and therefore how it behaves. So when you see alumina 2% on titanium dioxide pigment, it's not necessarily all one type of alumina, and no 2 grades with alumina are generally the same. And this is a little bit of the trade secret that the only one that titanium dioxide manufacturers perhaps still have is some of their surface treatments in order to be able to develop some of the improved dispersion stability properties. There's 2 types of silica. There's a fluffy silica, which basically generally improves the dispersibility, and especially for waterborne paints. But this fluffy silica can also be used in some of the grades that you may not see that much in the African market now, but which were prevalent in Europe and the US about 10 or 20 years ago, where they essentially use this silica to increase the oil absorption of the TO2 to essentially create a TO2 with a partial dry hide effect. Now, so that fluffy silica will be used for that. That's the time when you're probably going to get 15% of the surface treatment when you have this fluffy silica. Grades like 931 from Chemours, 2044 from Kronos, those are the ones that have that sort of grade, that sort of silica. But there's also a dense silica, a different type of silica, which is gives a similar chemical behavior in waterborne because it introduces negative charge to the TO2 in the water, but it's used almost like a pair of sunglasses on the TO2 in highly durable applications to help preventing UV light getting into the TO2 crystal. And so this dense silica, I'll talk a little bit a bit later about the mechanism of how the UV degradation works. But these grades with dense silica on tend to be used in the very high-end, highly durable applications like architectural powder coatings, automotive paints, things like this, and things like R960 from Chemours, and I think it's 696 is the grade from Tronox, which actually have this super dense silica on that give a very, very high durability. Zirconia is used for durability improvement, but works in an entirely different way to the dense silica. The dense silica is like sunglasses. It wants to stop the UV light getting to the TO2 and having free radicals produced inside the TO2 that can break down the polymer. What zirconia is a free radical scavenger. And so by putting zirconia on the TO2 in small quantities, they manage to scavenge the free radicals as they're produced on the TO2 inside the TO2 crystal to a degree so that it reduces the effect on the polymer when this happens. And so most multi-purpose grades of titanium dioxide and all durable grades of titanium dioxide will have some zirconia present in order to be able to do that. Finally, there's a bit of hydrous TO2 and some phosphate. These are generally used in relatively small quantities compared to the other grades, the other treatments, but will be used to fine-tune the performance of the titanium dioxide surface treatment and hence differentiate the grades as they're produced. Little picture about what to expect or what they look like. You know, a general purpose titanium dioxide that you'd have just alumina, maybe a little bit of alumina and some dense silica here would look a little bit like that. You can just see the surface treatment on the outside of the particle. Your heavily coated TO2, like your R931 from Chemours, has this fluffy silica and alumina on the outside. You have some super gloss TO2s like TO92 that Billions sell now, and RDIS that's sold by Venator that has just a very, very small amount of alumina. And this is the super durable pigments with the dense silica. So you can see you have a lot more surface treatment and it's very dense. It's not diffuse for exterior paints and automotive. So now talking about dispersion of TO2, essentially when you're trying to disperse it, like with any other pigment, you're trying to break the chemical bonds holding the particles together and then stabilize them, okay? Once you disperse them, you're trying to stop the van der Waals attraction, pulling them back together. And if you pull them back together, gravity is what's going to make the paint settle. So the process of dispersion is about breaking something up and then attaching something to the pigment particles so that they become stable and don't settle out. Because nearly every pigment particle, TO2 has a density of 4.2. If anything, it wants to settle into the bottom of a paint can. So you need to introduce something to keep it stable. And dispersion can be achieved in a number of different equipments, depending on the application that's trying to go. You can look at a ball mill, which is very high impact and low shear, or you can go to the other extreme where you've got a very high shear impeller mill, which is how most really good coatings are made now. Some of the inks and things are still made on 3-roll mills, and there are people still using ball mills, nutrition mills for certain applications, but most of the high volume applications have moved to these more highly efficient, higher technology mills. And it's on the high speed impeller mill is what I'll assume that most people are using. Now, a few notes about dispersion stability, and could talk about this for a long time, but essentially it's important to understand that in solvent-based systems, essentially you don't have a lot of polarity. So you're looking to have steric stability. You want your dispersant or your polymer to create this little steric area so that particles don't bump into each other and the van der Waals forces pull them together. Whereas in water-based system, you get everything is polar, everything is charged, and you manage the stability of the TO2 and the lattices and everything with the charge on the surface. Okay, and it's important to understand those two things, very, very different. So when you think about solvent-based systems, the requirements for steric stabilization is you need to have a full coverage of the surface to avoid bridging, and a strong anchor for the dispersant or the dispersing resin in order to attach it to the pigment surface. And when you say strong anchor, it doesn't all come from the resin. This is one of the reasons the TO2 surface treatment exists. It provides, you could say, the basis for which to anchor to on the titanium dioxide surface. You need to have a polymer and TO2 that has an adequate layer, and essentially what you end up with is sulfated polymer around the particles that essentially creates this steric area that gives you stabilization. When you think about the effect of the TO2 surface treatment, you tend to find in solvent-based systems, alumina is far better than silica, because silica has a kind of an acid surface and it tends to draw the polymer flat to the surface. And so you get less steric stabilization, whereas alumina, and especially the way it's applied in the TO2 to the TO2 surfaces, essentially as a basic surface, alumina being amphoteric, and so you end up with a much better attachment of the polymer to the surface. And so you tend to find that in general for solvent-based paints, alumina treated products are better. Mill-based design for a solvent-based system. Essentially, if you're using a high-speed dissolver, you can't really avoid doing this. If you're using any sort of old-fashioned mill, you probably could. But essentially, there's a method out there called the Daniel flow point method, which allows you to evaluate for a given titanium dioxide or a given pigment the amount of resin you need to actually properly wet and stabilize the pigment. I won't go into the detail of what this is. You can look up the method even on Wikipedia, I believe. but I would advise everybody who isn't doing this to do this if you have any problems with titanium dioxide dispersion or stability. This is the back to basics on how to make titanium dioxide disperse and stable in solvent-based systems. In water-based systems, as we said, it's all about polar. Everything is about charge. And you can actually measure the charge on particles in water, whether it's particles of latex or pigment or whatever, and measure the charge that you get at a certain pH is called the zeta potential. And essentially, you just got here a graph of what zeta potential is in millivolts and the vary in the pH for a certain type of particle. And you can see you've got two different alumina particles, silica particles. You can see they behave entirely differently. And so silica is always negative. Alumina being amphoteric can be either positive or negative. So you can start to imagine how skilled the titanium dioxide surface treatment chemists have been in when they're designing their products to create products that give different characteristics in different formulations. Now, when you use titanium dioxide in water, you're going to use a dispersant, generally a polyacrylate. Now, you can use some others. And what you're looking to do is produce a negatively charged cloud of salted polyacrylate around the CO2 particle that is itself attached to the titanium dioxide particle surface. Now, having the right amount of dispersant in a water-based system is really, really important. And a little bit like with the Daniel flow point, which is a very empirical method, you can actually do some measurements with different dispersants and different titanium dioxides called dispersant demands to understand the interaction between titanium dioxide and the different dispersant. If ever you see you're changing a dispersant or changing a grade of titanium dioxide and encounter a viscosity stability or a pigment stability issue, the likelihood is because of the different interaction between the dispersant, a different dispersant and a different titanium dioxide. And just to give you a couple of examples, two different dispersants here on the same pigment. You can see the amount of dispersant is entirely different. This dispersant demand test is essentially done by measuring the viscosity in centipoise whilst titrating dispersant into a slurry of titanium dioxide. I think the methods, again, are available if you want to Google them. If you can't find them, we can probably explain them to you. But if you have an ICI rotary viscometer, it's very, very easy to do a titration of dispersant into a pigment slurry and plot a graph like this to characterize TO2 and dispersant. In general, having done this, you tend to double the dispersant level, and that's the level you need. Now, whether it's water-based or solvent-based, if you're using an impeller to mix, which most people will be for decorative and industrial coatings, it's absolutely critical to make sure that the geometry of the mixer is correct and the rheology of the mill base is correct in order to disperse titanium dioxide. That's not the reason for this part of the lecture, but I just want to make sure that everybody understands. If you have a dispersion problem with titanium dioxide, it may not be. It's very likely your wheel bases are too low viscosity, or your impeller's too low, or all of these things add to the performance you're ultimately going to get to the titanium dioxide if you do them properly and understand what's going on. So having done all of that, problems with dispersion of titanium dioxide, we spoke about flocculation. Flocculation is when the titanium dioxide dispersion isn't stable and the van der Waals forces pull the titanium dioxide together. So essentially you have areas of crowded titanium dioxide and areas where there's no titanium dioxide. Okay, so you have a region with no opacity because you don't have the stability of the dispersion. And when you look at the reflectance of light on paints that are perfectly dispersed and flocculated, you can actually see that there's less light reflected in the visible from the flocculated paint. And interestingly, because you're essentially creating little clusters of TO2 that have an effective higher scattering particle grouping, you start to scatter red light greater. So out in the infrared, you can actually see that there's more infrared light being scattered. And so essentially, as I said, you get lower opacity because you're scattering less white light, but you're scattering more in the near IR. And Venator actually, when they were dioxide, developed a method for actually measuring flocculation by looking at the near IR of the performance of TO2, the flocculation gradient, they used to call it. But essentially, the big conclusion is that to get proper and you have to have proper stabilization and dispersion, whether it's solvent-based or water-based, of the TO2 in order to get the value from the product which you purchase. Cracking on now, just in towards the end, I know I'm running out of time. Some of the other properties of TO2, you'll all be aware of color and measuring color using the C-Lab system, you know, L, A, and B. Titanium dioxide isn't quite pure white. When you buy titanium dioxide, it's around about 98 or 99 L value with a value of something like 0.4 and a B value of 1, you know, depending on whether it's chloride and sulfate. Okay. But the important thing is that there are some subtle differences, as I said, right at the beginning between certain grades of titanium dioxide, either whether it's chloride and sulfate, or because of the level of surface treatment you have. You can imagine if you have a lot of surface treatment, you have a little less titanium dioxide. So the actual optical performance may vary because of that. What you tend to find is that for color, for mass tone, the critical applications are, you know, kind of, you know, automotive can coating, coil, powder, and then the less critical ones are the areas where the polymers or there's a lot of fillers used, and those fillers themselves have some color. So essentially, when you think about it in a resin sense, if you have a super clear resin, like in an industrial application, okay, if you use a lower quality TO2 that might have a little bit of iron in it, slightly yellow, you're going to see the difference because the resin is clear, okay? If you're making a decorative coating using an alkyd resin, that alkyd itself is ever so moderately yellow. And so a yellower TO2 actually isn't going to be as obviously seen as a chloride TO2, perhaps, that has better color. And you can actually, you know, the human eye will only be able to see a delta L, a delta B of about 0.2, maybe even 0.3. And so when you actually look at some of the color differences, and this is a really interesting chart of the color differences from the different types and grades of TO2. If you're in a decorative coating, like an alkyd paint, there's very little difference even between an average quality sulfate and a very high quality Western chloride. You know, this difference is 0.4 L, so you just about see it. Whereas in an industrial coating, when you have a very clear resin and acrylic melamine, something like that, you see the difference with the same pigments is actually more like 1.5 units of L. Okay, and that's why the chloride process pigments tend to be used in these sorts of higher end applications, and why the sulfate process pigments tend to be used everywhere else, because you almost can't tell the difference there, and the sulfate pigments are generally much cheaper, as I'm sure you're aware. Tinting strength is related to the whiteness of the TO2. If you look at two different tinting strength TO2s, you're going to have you know, different degrees of whiteness, and that's in relation to the the way the particle is built and the size of the particle. So essentially, the scatter efficiency of the TO2, how many particles are at that perfect D50 for the 280 nanometers, will determine the strength of the white light scatter. So just to give you an idea here, if you have some TO2 that's got a really nice particle size and they're all of the right particle size, you get a lot more white light scatter than you will when the TO2 has a more variable particle size. Okay, this is a bit of an extreme, but it emphasizes the difference in tinting strength. You'll also see a difference in tinting strength because of differences in surface treatment amounts as well. So certainly if you're below CPVC in a paint, if you're comparing a paint with a very high level of surface treatment that might be super durable with one with a low level of surface treatment that isn't, you may well see a difference in tinting strength just because of the amount of TO2 actually in each particle. Undertone is really important to color. And essentially, this is quite difficult to explain, but essentially represents almost, when you think back to what I showed you on flocculation with the clusters of TO2 scattering more red light or infrared light, deviations in the particle size of the TO2 can lead to differences in the color in the presence of an absorber like a carbon black or a blue or something like this. And what you can see here is the drawdown. You can see a kind of a gray and a kind of browny gray. And what you see here is the scattered wavelengths change with the particle size of the TO2. Okay. There used to be so essentially the smaller crystal, you're going to scatter more blue light. With a larger crystal, you're going to scatter more red light. So variations in quality can lead to differences in this undertone. And you tend to find that chloride processed pigments give slightly better quality undertone. Sulfate processed pigments are perhaps a little bit more variable. But in general, good suppliers will control this property. But if you're making a color mixing system, it's really, really important that you have a pigment that's going to have reliable undertone. Because if you have, again, looking at this simple schematic, different size TO2 particles from one batch to the other, you're actually going to refract more blue and more red, even though the amount of color is the same and the whiteness of the TO2 looks the same. When you look at it in the white, you're actually going to scatter different wavelengths of light. And that's why when you're making a mixing system, it's absolutely critical. Gloss, and I'm running late here now, so I'm going to probably skip over gloss. Gloss is about the particle size of the TO2. Okay, can be affected, will be affected by flocculation, but different paints have different gloss requirements. That's the important thing. So in a really high gloss paint, when you've got no fillers at all, you'll see finer particle size TO2 will have a better gloss. Chloride will be slightly better than sulfate. As you go into semi-gloss paints and matte paints where you've got fillers, you're going to see that these differences, you cannot see them. Again, which is why in primers and matte paints, sulfate processed pigments tend to be able to use alongside chloride and therefore much cheaper to use than elsewhere. And just looking at the effect in glossy paints, the effect on gloss, when you look at the particles above 400 nanometers, you can see that it is a critical factor for titanium dioxide. And in the automotive paints where distinctness of image is absolutely critical, you find that only chloride pigments tend to be used. Or in the inks applications where you have a very, very thin film and a high level of gloss needed, they then have a very, very specially milled pigment. Happens to be sulfate because of the nature of the process, but this is a very low surface treatment and special product in order to get the high gloss in inks. And finally, durability and weathering. This is fundamental to titanium dioxide because in general, all of these problems that you can see from durability with this mass loss, color change, chalking, cracking, dirt retention, a lot of it is related actually to the titanium dioxide in the paint. Essentially, there's two things you have to consider when you're thinking about about paint degradation. One is basically, is your polymer going to be durable enough? If the polymer isn't very durable, you're going to find that the polymer will break down. Okay, and this is often the case in very cheap alkyd paint, where the polymer breaks down, the effect of the TO2 or anything else in there is minimal. However, as the polymers become more durable, okay, the titanium dioxide itself has a part to play in causing the degradation of those polymers. The TO2 can be the host for forming free radicals, and those free radicals go on to break down the polymer chain. This is the science. Essentially, you have, don't go into too much detail, but the UV light causes an electron to be elevated and a free radical to be produced either with water or oxygen, can go on to break down the polymer or the color pigment, which is where you get the color bleaching coming from in certain pigment systems, especially with organics. So you end up with a chemical reaction caused by the UV light catalyzed by the TO2. There's different ways of measuring exposure. I'm sure you're all aware of that. But the thing I wanted to get to quickly is that the different types of TO2, you remember I talked to you about the surface treatments and how those different surface treatments, some of them can give you sunglasses for super durable, some have zirconia for highly durable, some have TO2 that might be uncoated, and then the normal alumina treated multipurpose TO2. These are durability performance. Again, I think this is a Venator chart that they shared with us, but essentially you can see that looking at gloss retention over 3 years in Florida in a typical paint, you can see that if you just have the resin, nothing happens. If you put uncoated TO2 into it, it's done in 3 months. That's the photocatalytic effect. Having some surface treatment on the TO2 improves it. Having some zirconia there improves it further. Having special silica, probably zirconia as well, you end up with a super durable TO2. That means you can get nearly 18 months where it's almost no effect whatsoever. So that's what you get from a super durable TO2Y. And I'm going to have to go quick now because I have overrun. And essentially, when you're looking at optimizing with TO2, there are various ways of doing this. And to be honest, I'll probably, because I am so late, I could probably invite Jenny to invite us back in a year's time or something, do optimizing TO2 as a separate subject, because that's the area that FP Pigments operate in. But we are prepared to be honest and talk about the other products that are used here. There are fillers and extenders. They operate by essentially just reducing the area that the filler denies to the TO2. So when you're trying to improve TO2 performance with a filler, you're actually looking to reduce the amount of the area that the TO2 can occupy the same volume as the filler. So by using a smaller filler, you allow the TO2 to be better distributed in the paint. Using a smaller filler will actually increase your cost and tends to increase your viscosity. So it's all a compromise for the formula, but some of these filler products are pretty darn good. And you can often achieve a really good paint improvements by choosing the right filler or blend of fillers. There are products that have, forced spacing of TO2 particles. Ours is one of them, where FP put TO2 inside a particle, so our TO2 cannot be moved. Evonik have a product called Evoke. There's a resin that spaces TO2 particles, but that tends to have some viscosity issues and it's very expensive. But these products work in addition to or on top of anything you can do with a filler. Okay, and so if you're looking to further optimize with new technology, you can look at this sort of technology to do that. Then there's the entirely another different type of product called where you're trying to put air particles into the paint, and these really only work in the matte paint systems above CPVC. Opaque polymer, Ropaque Ultra E is the big one that's sold by Dow. They introduce particles of 300 nanometer polymer that essentially create beautiful air voids inside the paint that again improve the light scatter. Flash calcine clay does a similar thing, but in a less organized way. It's possibly a little cheaper, and but both of these work in a way that's in addition to the fillers and in addition to what you might achieve with FP Pigments or something like Evoke. So they're all different ways to try and improve titanium dioxide performance. You can increase opacity by just putting air into the film, taking polymer out or increasing the extender level. Okay, you'll get more air like that, but the consequence is you reduce the scrub resistance and you're going to increase the film porosity. Essentially, you've made a different paint. And so this is actually my last slide. I'm surprised I only overshot by about 5 minutes. But essentially, if you are looking to reduce TO2 and mess around with the fillers or change, do a porosity test. Do a gilsonite stain test after you've done the opacity and actually check that you have the same porosity. Because otherwise, you're going to find that your customers aren't going to be so happy that you've given them a paint that's a far inferior quality. Now, my apologies for going so quickly. I tried to get in everything. I probably should have said at the beginning that this is essentially a 2-hour short course that Paul and I designed for a couple of exhibitions that we attended last year. Anything or any questions that anybody has, please feel free to ask them or to email us directly via fppigments.com. You can actually find mine and Paul's email addresses there. And thank you very much to Jenny and Oka for inviting us to do this. And my apologies for overrunning. So.
Okay, thanks very much, Andy. You did forget to mention that Serina Trading is your local agent.
I did, yes. Sorry.
Other hat, I have to mention that.
Yeah.
So you could get hold of me if you want to ask Andy any more questions. Nobody's written a question down yet. If you do have one that you'd like to ask, please quickly ask it. But I do have a question for Andy. Obviously, your point was clearly made that one of the first things you need to do is to make sure that you have dispersed your titanium optimally. Now, you showed us that you can measure reflectance to see if it's not dispersed optimally, but not everybody has a spectrophotometer in their lab. Is there any sort of rough way of finding out whether you've still got flocculation in your system or not?
I think in all fairness, most people formulate paints on an evolutionary basis. So they will take the formulation they have and they will change something. Okay. And essentially the acid test is essentially, if you want to see if you have something like flocculation, is the opacity up or down? Has the color changed a little bit? Because you get a little bit of metamerism, it'll be a little bit slightly redder, ever so slightly, if you've got proper flocculation. But you'll see a big difference in opacity. Flocculation isn't a kind of it's not so much a gradual thing. On your storage stability, you will see very clearly if the paint is flocculated on storage when you measure the opacity. I think the idea of flocculation gradient that dioxide put about in I think it was as early as the 1980s is a great way of putting numbers onto that, which means if you're doing a very large study, if you're looking to develop grades of titanium dioxide with different flocculation parameters, kind of that's the sort of tool that you would use. I don't know of anybody outside of the big multinational companies that might be using something like that. Most people will look at the opacity and then the opacity after a month's storage at a slightly higher temperature. And that's really what you would look at.
Okay. And then I wondered whether you wouldn't mind being close to the titanium industry as you are, and the rest of us sitting here at the end of Africa. Could you look into your crystal ball and give us what you expect to happen to the titanium price this year coming? And how it will affect South Africa? Yes. Are we going up, down, or sideways?
It's difficult to say. You benefited for the past 5 years, apart from the little hiatus we had when all the boats were in the wrong place after COVID, of Chinese prices driving down the TO2 pricing to Africa. Okay, in the prior to that, there was a plant in Umbogtwini, and all the other material sold in Africa came from Chemours or from Europe. Okay, And that was so you had a European company and European prices. So the titanium dioxide price over the last 15 years into Africa has dropped massively to somewhere around about $2, $2.50 out of China. And it's largely coming from China, apart from in those high-end applications where you need high-quality chloride, or it's spec'd in. Maybe you're buying a paint from Kansai, you're formulating under license. But essentially what's happening now is, the Chinese are continuing to expand their production. Nobody else in the world is expanding production. So all of the future titanium dioxide expansions are coming in China. So whereas I showed you a chart saying that half of the TO2 made in China is half the TO2 in the world is now made in China, in 5 years' time, 60% of it will be made in China, and the market will be 10 million tons. The problem is that China as a country and for all sorts of industries no longer has cheap labor, can't support the government, that can't have government subsidized industries forever, and is now having to be environmentally compliant. So the cheap Chinese prices that people enjoyed from 2012 to maybe 2020 are now actually impossible for the Chinese to sustain. And you will have seen in the past 5 months that the Chinese TO2 price has gone up by about $400 FOB Shanghai. Prior to that, the Chinese were not making any money at all collectively. There might have been a few making a bean and a few losing a few, but they weren't making any money at that $2 FOB price. And titanium dioxide, as I hope I showed you at the very beginning, when you look at the size of the plants, those chloride and sulfate plants are the same in China as they are in Europe. They cost just as much to make and maintain. They have to be rebuilt every few years because the chemistry and the temperatures is so aggressive. And so the Chinese are now getting hard, let's say, on actually trying to make some money from TO2. Now, so you're seeing a will from the Chinese producers to put up price. And they've managed to put it up now, and it's now been stable for a couple of months once they put it up. Now, that's going to be complicated by the fact that Europe very soon is going to issue an anti-dumping tariff against China, similar to what the US did when Mr. Trump took over there, but for different reasons when he did it. And so you're going to see Chinese TO2 carry a 20 or 30% duty on the way into Europe. Now that will mean that a little less Chinese TO2, about 50% of the European TO2 comes from China now. That will be more, won't go there, but the Chinese may want to sell it somewhere else. But India is also talking about an anti-dumping tariff against Chinese TO2. Now the problem comes is that if that happens, then a million tons into India and best part of 700,000 tons into Europe in the next 4 or 5 years will be at a higher price. But it'll still be at almost loss-making price for the Chinese because the tariffs will be paid to governments, not to the sellers. And so, if China tries to sell that extra TO2 they can't sell at low prices, they're not going to make any money. And so, from my analysis, is that the price that the Chinese are currently at, about $2.50 FOB Shanghai, is where they would. That's their new bottom. That's where they'll try and keep it if they can. And they'll want it to push it a little higher if they can as we go forward. So I wouldn't ever anticipate Chinese prices falling massively from here. TO2 always goes up and down, okay? But it's not going to go down to less than $2 again out of China, ever, I think is. And depending on economic activity, it could go up above 3, but that would depend on so much good news. We'd all be making so much of other things. It wouldn't be so much of a problem. I think that's my spin.
Very interesting. Thank you. And I think the South African market has benefited from the import duty being scrapped after the upper plant closed. And also the rand is stronger at the moment. But who knows what's going to happen after the elections. So again, we're in for a rocky ride, I think. Anyway, thank you very much, Andy, for your time. It's been very interesting, and I hope everyone on the call has been learned a lot about titanium dioxide. A very good overview of the whole story about titanium dioxide.